In this example, we're going to be determining if a given matrix is linearly dependent or linearly independent. Here's my matrix. So I'm going to write down 5, 3, 4, 10, 7, 8. I promise that's a 5. 15, 4, and 13. So in order to figure out if this matrix is linearly dependent or linearly independent, we need to see if the equation A times what I call the x vector equals a 0 vector, if this has a solution other than setting all the x variables to 0 or not. In other words, does it have a non-trivial solution? If it has a non-trivial solution, that is, not all my x's are 0, then it means one of these vectors can be written as a multiple of the other, and it therefore means that this system is going to be linearly dependent. They're not all perfectly unique vectors in terms of describing a plane or a line or space. However, if the only solution is the trivial solution, all zeros, it's going to be linearly independent. So how am I going to go about figuring this out? Well, I'm going to go ahead and write the augmented matrix that corresponds to this equation. And so now, even though when I first write my matrix, I'm thinking of column vectors, and so I write them this way, now I'm going to think of systems of equations, and I'm going to write this way. So I'm going to say out loud what this matrix represents as I write it. This is going to be 5x1 plus 10x2 plus 15x3 all equals 0. So there's my first equation. My second equation is 3x1, 7x2, 4x3 all equals 0. And my third equation is 4x1, 8x2, 13x3 all equals 0. Now, we're going to go ahead and do row operations to solve this. Anything you can see to simplify, you're going to want to do that first, because especially where I've got something here with two-digit numbers like 13, I really don't want to multiply stuff by 13. And I doubt you do either. We can if need be, but if we can avoid it, we want to. And so the thing that sticks out to me is that this top equation here is divisible by 5. And so I'm going to go ahead and do that. It's great when your right-hand side is all zeros because you can just kind of blindly do your work and not worry about this column, which you shouldn't do, but you can get away with. Nonetheless, I will announce what's happening over there. So if I divide this top row by 5, I get 1, 2, 3, 0. Now what I like to do is once I've changed a row, just to save me writing, is I go ahead and look at my new row and then look back over here and see what I would do to that. So I'm just mentioning that. I'm not going to do that to you though. I'm just going to go ahead and rewrite everything. So 3, 7, 4, 0, 4, 8, 13, 0. And now my first step is to get rid of this 3 and get rid of this 4. Well, that's super convenient when the number above is a 1, because literally all I need to do is subtract 3 times row 1 from the second row, and subtract 4 times row 1 from the third row. See that 3 minus 3 times 1 will be 0, and 4 minus 4 times 1 will be 0. And then I'll figure out these other values as well. So let's go ahead and do that. Top row is not changing, so I'll just rewrite it. Okay. So 3 minus 3 times 1 is 0. 7 minus 3 times 2 is 7 minus 6, which is 1. 4 minus 3 times 3 is 4 minus 9, and that's going to give me a negative 5. And this is all 0. 4 minus 4 times 1 is 0. 8 minus 4 times 2, well, that's 8 minus 8, which is 0. 13 minus 3 times 4 is 13 minus 12, which is 1, and then 0. Now, if you're good on your theory here, you can see we actually already know that this is going to be linearly independent, because look at what I've got here. x3 is 0. And if you look at this equation, this means x2 minus 5x3 equals 0, but x3 is 0. So x2 also has to be 0. Likewise, x1 is also going to be 0. So this form of the matrix here is called echelon form. And what I'm about to do is I'm going to do all the work explicitly, and so I'm going to get this into row reduced echelon form, which means the only numbers I'm going to have in each column are ones, and then it'll be really clear. So let's go ahead and do that. So my first thing is going to be add 5 times row 3 up here, and subtract 3 times row 3 up here. What's nice about getting this into echelon form, where we've just got the ones, is that when I multiply this by stuff and add it up, it doesn't affect these other 2 columns. So I can just eliminate these right here without worrying about those. So I'm going to have 1, 2, 3 minus 3 is 0, and then these columns aren't being affected. This 0 column's not being affected. Negative 5 plus, ooh, I forgot to put a 5 there. Boop, boop, boop. Negative 5 plus 5 times 1 is going to be 0, so 0, 1, 0, 0. 0, 0, 1, 0. And last step, simply subtract 2 times row 2 from the top row. Notice I couldn't have done that here because it would have changed this number right here. But now I can do that with no worries because those are just zeros, so nothing happens. So this is going to be 1. 2 minus 2 is 0, and then 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. And so the thing is, it looks like, hey, we got a solution. So they're linearly dependent because we were able to solve it, right? Yeah, but what was our solution? If we look at what the solution is that we got, we've got x1 and then nothing equals 0. We've got x2 and nothing else equals 0. And we've got x3 and nothing else equals 0. Yeah, we got a solution, but what is that solution? All my x's are 0. This is the trivial solution. Since this is the trivial solution, where all my x's are 0, this equation only has the solution x equals the 0 vector, and therefore this matrix right here is linearly independent. None of these vectors can be written as a multiple of the others. And that is this example.